one particle in a quantum oscillator and a particle striking a square band. Okay, so I hope that with these three problems you developed some concepts regarding how quantum mechanics is used to predict the behavior of particles at the quantum scale, at the small scale. What you do, you have a potential which specifies the problem. You substitute the potential into Schrodinger equation. You solve for psi, and once you have the wave function, from wave function you can find information like what's the energy of the particle in a stationary state, and if a particle strikes a barrier, what's the probability of its transmission, what's the probability of its reflection, and in a quantum oscillator we did the same, almost the same. We have only confined ourselves to one-dimensional problems, even though most real-world problems are three-dimensional. But the numerics change when you go from one to higher dimension, but the concepts more or less remain the same. But since we don't have a very high mathematical background right now, we didn't attempt the 3D quantum mechanical problem. Today, I will revisit hydrogen atom again and hydrogen-like atoms. The actual solution, quantum mechanical solution, actually comes by solving the three-dimensional Schrodinger equation, which I will not do because the mathematics is too advanced for many of you, and since my goal in this course especially is to take everybody along, so I'm trying to keep the level of mathematics low. So what I will do, that for hydrogen-like atoms, I will simply state the results, most of them, and try to give you some intuitive meanings and reasons that why the solutions are like this and why the behavior is like this. But of course, to get the actual answer that why, let's say, the energy levels or quantum numbers are like this, you have to solve this Schrodinger equation, which we will not. Actually, and even if we solve three-dimensional Schrodinger equation, there are still many problems that we are leading to very high and advanced physics. For example, we know the stationary states. For example, in a one-dimensional quantum world, the electrons or other particles can be n is equal to 1 state, they can be equal to 2 state and 3 state. So if we have a particle in n is equal to 1 state and a photon comes, it can absorb a photon. If the photon's energy is equal to the gap between the two states, it can go to the higher level state. And we know that after some time, the particle jumps back to lower energy state again. Why do they do that? We haven't attempted this question, and we will not be able to do it for a long time unless we study the full relativistic quantum electrodynamics, where we combine quantum mechanics, relativity, and electrodynamics together. Where we see that there are background vacuum fluctuations of energy. For example, even in vacuum, which you might initially imagine to be as a space which is void of everything, is not void of everything, because of uncertainty principle, there are small fluctuation energy going on everywhere. For example, the particles being created and then annihilating, then creating, and so on. So those background fluctuations force particles in higher energy state to jump down to lower energy state again. So these types of things. And also, for example, for the tunneling problem, we said that, okay, a particle is coming from here, and then there's some probability of it tunneling through, and then some probability of it reflecting back. And then we model particle in a nucleus going back and forth, even though that we know that calling particle and a particle and working with it like this is not completely quantum mechanical. But we have to live with our level of the course and mix classical and quantum mechanical treatment of particle and wave to get some basic concepts of how world works at quantum scale. In the same way, so today we will quickly review hydrogen-like atoms and actually in just 5 to 10 minutes after reviewing, because I know you have done these things in your chemistry course as well. What I will do is actually go on to introduce the concept of spin and its importance and what are its consequences in multi-electron atoms and in other phenomena. Actually, very crucial in understanding a lot of things. For example, you see my hand pushing on this aluminum rail on the board, while my hand is not sinking into the rail. You are all sitting on the chair, why aren't you sinking down? Why isn't everything being pulled towards the center of Earth right now? What is holding everything in place? Can you guess what it is? Gravity is pulling everything to the center of the Earth. Okay? Yes, that's one good answer, but why are then, let's say, positive and negative charges just collapsing onto each other? So one simple answer is that it's quantum mechanics. Yes? Space-time what? I didn't actually quite get what's the logic that you're putting in. But if you, let's say, see everything in terms of atomic world, you see materials are what? They have different atoms arranged one next to each other. And an atom is, if you imagine, the nucleus and there are layers of electrons. Why aren't all the electrons collapsing onto the lowest possible energy state? Because of Pauli's exclusion principle. It says that no two electrons can have the same set of quantum numbers, or they can't have same quantum state. It actually comes from spin. And that's what we will talk about in this and the next lecture. Anyway, so let me review hydrogen-like atoms. Hydrogen-like atoms are atoms with a nucleus containing Z number of protons and only one electron. Actually, this is the only type of atom that we can analytically solve. More than one electron around the nucleus, or imagining nucleus to be more than a point particle, we can solve the Schrodinger equation completely analytically. We have to resolve to approximate numerical solution. So, the actual way of finding the possible stationary states of an electron around the nucleus is that you solve this Schrodinger equation in 3 dimensions. Let's say x square and then z square and y square for the given potential in which this electron is, and the potential is the same as we already know, K, sorry. So this is the Schrodinger equation. Okay. So to find wave function associated with any particle, you have to solve the Schrodinger equation. We are not going to do it. I'm just reviewing briefly how do we solve it exactly. And the way to solve it is that you can express the unknown wave function psi as product of, let's say, 3 parts. One part that only depends on the radius, the other part that only depend on, let's say, an angle with some axis z, and another part with another angle with a third axis, for example, in spherical coordinate system. Because this problem has spherical symmetry, so our wave function can be broken down into 3 parts. So you put into this, you separate variables, and you get 3 equations. You solve those 3 equations, and you find these radial, azimuthal, and this phi dependent parts of the wave function, and during the wave you also find the expressions for this energy. And when you solve it, you get this. The energy comes out to be 13.6 Z square n square electron volt approximately. And so let's put a sub n. It depends on n. So this Z is the number of protons in the nucleus, n is the number of the energy states, so n1, n2, n3 and so on. But not only this, we also find other information. क्योंकि जब इसको solve कर रहे होते हैं, तो we need several integers to uniquely specify the solution. For example, उन्होंने say किया है कि we require the wave function to be periodic in theta. तो उसमें जब हम periodicity assume करते हैं ना, तो फर्क करें periodic function है sin, cosine वगैरह. तो जो sin, cosine function उनकी argument में जो theta होता है, अगर हम चाहते हैं कि after every revolution the function has to have the same value, theta should vary in integer multiple of 2 pi. Similarly, the phi dependent function have to have integer dependence. वहां से दो integers हमें हमारे पास और आते हैं, और वो integer उनकी basic logic ये है कि जो ये psi wave function है, it has to be periodic in theta and has to be periodic in phi. क्यों? क्योंकि 2 pi के बाद physically we reach at the same point. So our function should be periodic in 2 pi. So in this direction and in this direction. So वहां से दो इंटीजर हमारे पास एक और आते हैं. One of them is called L. So L can have value anywhere between 0, 1 up to n minus 1. So for example, if n is 1, L can only have a value of 0. For n is equal to 2, it can have value of 0 and 1. And then there's a second integer, ml, and this can have values starting from minus L to L. D. This is the potential that this electron is feeling. K electron charge, nucleus charge over the distance of. अब E square कर, E into E और E square एक ही चीज होती है. Is that okay या not? ठीक है, तो मुझे पता बात का अक्सर बुक्स में ये Z E पहले लिखा होता है E square. मैंने जानबूझ के इस तरह से लिखा है कि you are reminded of the fact that this term is product of two charges, one of electron, the other of nucleus, and the nucleus has a charge Z into E. And this R is the distance between the two particles, and this is x square plus y square plus. So, periodicity ये कहती है कि जब आप एक revolution पूरा करें, तो जो आपका function है, it should be periodic. ठीक है? Let's say आपके पास solution इस तरह क्या आ गया? Sin some a theta. अगर ये a ना हो या a1 हो, तो इस फंक्शन का पीरियड कितना होगा? 2 पाई. तो ये अगर किसी चीज को रिप्रेजेंट करता है तो 2 पाई के बाद इसकी सेम वैल्यू आ जाए. लेकिन इसकी वैल्यू 0.1 कर दे, तो ये इसका पीरियड 2 पाई नहीं रहेगा, बल्कि 2 पाई का मल्टीपल भी नहीं होगा. अगर इसकी वैल्यू 2 हो जाए ना, तो फिर भी काम ठीक. 2 थीटा जो है, this is periodic with period pi, और जो pi period है, it is still periodic with 2 pi as well. कि after 2 pi rotation in angle, you still get the same value of it. तो इस तरह के इसमें इंटीजर्स आते हैं. इस तरह जो phi वाला पार्ट है, उसको भी सॉल्व करें तो sin, cosine जैसे उसमें phi वाले पार्ट में इस तरह क्या. So this is also cosine phi plus sin phi. Phi is this variable. So let's say this is x-axis, this is y-axis, this is z-axis. तो अगर spherical coordinates में देखें, तो किसी भी पॉइंट में कोऑर्डिनेट होते हैं r, which is the distance from the origin, theta. This is the angle of this line with the z-axis, and then phi is the angle of the projection in xy plane with the x-axis. So कार्टिशियन कोऑर्डिनेट में किसी भी पॉइंट को आप रिप्रेजेंट करते हैं x y z 3 पॉइंट्स, स्फेरिकल कोऑर्डिनेट्स में उसी पॉइंट को आप r थीटा phi से रिप्रेजेंट कर सकते हैं. So even if you don't get where they come from, it doesn't really matter much. If you can remember this, but as I said earlier, that I'm trying to review where they come from, but unfortunately we are not going to solve it. I'm coming to that. So for each value of this integer, you get one unique wave function psi. Okay, and let me say something about those psi's for a few of them. Let's say for n is equal to 1, so L is only 0 and ML is also 0. So there's one other information that I have left out, I'll come back to it. So this psi 100 is something, some function. We don't have to worry about it. लेकिन अगर इसको हम इसका स्क्वायर कर लें, so this gives us the probability density, and it depends on r, theta, and phi. And it turns out that for this function, it's independent of theta and independent of phi, and only depend on r. और अगर मैं अभी देखें ये फंक्शन है r, theta, phi का, इसको प्लॉट करना जो है, you need 3D and even actually you need 4D. To represent 3D, you need 3Ds to represent 3 independent variables, and then you need the fourth D to represent the magnitude. लेकिन इसको दो तीन तरह से लोग represent करते हैं. Some people would draw a circle, but this is slightly misleading if you don't know what it means. A better representation is some people would draw this cloud, but then the density of cloud is such that it's denser somewhere around here, and it's rarer here and here. So this is actually, and you can imagine it in the spherical form. So this tells us that electron is most likely to be found anywhere from, electron is likely to be found anywhere from here to here, but it's most likely to be found here than here. और अगर मैं सिर्फ वर्सेस r इसको प्लॉट करूं इस psi 100 square को, so this is something like this, and this is called 1s, this psi 110. So this says a electron can be found anywhere, essentially from r equal to 0 to r infinity. Now this is in contrast to Bohr's model that we have in mind, that electron is going around in a fixed orbit. और इसी को equivalently of some, or fortunately there is a correspondence with Bohr model like this, that this distance of being of the highest likely place is still the first Bohr rate. So when I plot this circle, this only means that electron is most likely to be found around here, but electron can be found here, electron can be found here. Everybody is comfortable with this thing? Okay, good. एक दो था. So let me go to the next one. So the next possible is n2. अब n2 में L can be 0, and when L is 0, ML is 0. So for this is called a 2s orbital. तो अगर इसकी probability हम सिर्फ r के अलावा देखें, this is something like this. I'll go to that. So this is the 2s probability distribution. और इसी तरह अगर आप n2 में L1 की बात करें, and ML can now be -1, ML can be 0, ML can be 1. So these are all called p orbitals. इन तीनों में जो फर्क है वो सिर्फ इतना है कि when ML is -1, the angular distribution is such that if the nucleus is here, the particle is most likely to be found in this region and in this region. क्योंकि तीन एक्सेस है x, y, z. So for ML equal to -1, it's like this. For ML equal to 0, it's the, let's say, y axis. and for ml is equal to the other one, it's the third axis. लेकिन इसका अगर आप रेडियल डिस्ट्रीब्यूशन देखें तो इट इज समथिंग लाइक दिस. मतलब कि ये एस वाला मैंने थोड़ा गलत ड्रॉ कर दिया, let me correct. ये बेसिकली ऐसे और जो P है, जो 2P है, it's something like so 2P has only one peak. This 2s has two peak, one small peak here and a large peak here. So when people draw this 2s orbital, they sometimes this is 2s. They leave this empty circle here to indicate that there is a null point somewhere here. But still, its most likely position is this distance, or symbolically, you can still draw it like a circle. So this is a bigger circle than the 1s circle. Let me draw it a bit bigger. So the 2s orbital, when it's drawn like a circle, it only means that electron is most likely to be found here than here. But electron can still be found here or here. We don't know and we don't care and it doesn't matter. अगर आप हंसते हैं तो let me repeat it. ठीक है? We don't know, we don't care and it doesn't matter. This is what quantum mechanics is. अब इससे शुरू करें. For an atom, what matters? You have to, in experiment, atom interacts with light. That's the only way it interacts with the body. And when it interacts with light, it absorbs a photon, and then it absorbs. Why does it absorb photon of only certain energy? For that to work, we need to know what's the energy in this state and what's the energy in this state. Okay? And we can do that with whatever information we get from quantum mechanics. So I know this is uncomfortable for many people, and it is unsettling in the beginning that we have to abandon the idea of knowing everything. That's no more true in quantum world. So that we can do. And if you have to do other things like what's the probability of this electron going from here to here, you can still compute that using only the knowledge of wave function. And आप ये सब सवाल इसलिए पूछेंगे आपके ज़हन में ये confusion है कि इलेक्ट्रॉन क्या कर रहा है, इलेक्ट्रॉन ऐसे जा रहा है, ऐसे जा रहा है, कैसे जा रहा है? We don't know and it doesn't matter. That's the way the universe is. That's the way it is, and we have to live with that. Okay. पहले धुआं नहीं करो. So we will work out those rules where the electron will go. Okay. So let me just continue a little bit. Similarly, when you see this type of orbital, this is the real way of imagining it is a cloud. Okay, but this is usually drawn like a figure 8, which only says that electron is most likely to be found here, then here and here and here. So yes, the nucleus. Yes, so even you see in the quantum mechanics, there's nothing that says that we are going to find the movement of electron. We are only going to find what's the probability of finding the electron at some place. There's another type of problem where we say that okay, if electrons are in this state, how the state evolves, how does it convert to the other state? That part, the time evolution, we are not concerned in this course. Okay, but that can be done. But even in that one, we don't know how the electron goes from here to here. We can know we can know how the wave function is evolving, but the wave function is giving the probability in a certain region, not at a certain point the electron yahan pe. So even in that, when we work in time evolution, how this 1s state converts to 2s by absorbing a photon, we don't try to see how the electron goes from here to here, how does it jump, does it go like this or does it go like this? So these types of questions are neither asked nor answered in quantum mechanics because they are irrelevant. Okay, so if we continue like this, we can construct what we call different states with different energies, and as you can see that even from this, the expression for energy is actually same and only depends on n. Energy is state की भी और state की भी same है. और इसी तरह जो next state है, this is let's say some p, so when n2, l1, ml can be 0, and when n2, l can be 1 and ml can be 1. So these four states are possible for n is equal to 2. For n is equal to 1, only one state is possible. But all these four states have the same energy. We call them degenerate states. The states have different spatial distribution. Their wave functions are different. The probability of finding electrons are different for all three states, but all the four states have the same energy. We call them degenerate states. So similarly, you know how to continue with n is equal to 3, 4, and so on. You can see the book. Let me now come to another thing which is equivalent to answering that question of what electron is doing. Is it going like this, or is it revolving, or what's the type of motion? When something moves, essentially the important quantity, the physical quantity that is associated with it is the momentum. When it moves linearly, there is a linear momentum. When it moves in a spherical region, there is an angular momentum associated with this. And when you solve this problem, the angular momentum is found on the way while solving this equation, and it is found that the magnitude of the angular momentum is, let me put a vector n bar to stress that its magnitude is given by this equation and what we call z component. But z component is only an arbitrary label. Any axis can be z axis, and the z component of angular momentum is given by this. So, for example, when the electron is in this state, it has an energy given by that formula, but how much angular momentum does it have? 0. Because L is equal to 0. When electron is in this state, it has a different energy, but still 0 angular momentum. In these three states, electron has the same magnitude of angular momentum, and that can be found by putting L is equal to 1 here under root 2 cut, but three different possibilities for the z component of the angular momentum. So it means the z component of angular momentum is quantized. And let me pictorially represent it. N is equal to 1 state, angular momentum is 0. So N is equal to 2 state, and when L is 0, magnitude is 0, and when L is equal to 1, magnitude is under root 2 h cut. So when we are solving this Schrodinger equation, they come out. So obviously, if you're interested, and they can see the book actually in chapter 6, it has been solved in up to, let's say, 70-80% detail, and the rest is in the appendix. But we have to skip that because a lot of us are not going to be comfortable with that. Okay, so let me now explain the status of z-axis and what does this angular momentum mean. It means that if you have an atom, and let me just represent atom as a whole atom, and you take any other axis, it can be pointing like this, it can be pointing like this, it can be pointing like this. And let me purposefully draw it like this and label it z-axis. You take one axis and you try to measure the angular momentum of electron in the atom. If the electron is n is equal to 1 state, you will measure it to have a 0 angular momentum. And no, you see there is a contradiction with Bohr's model right away. No, it may be moving, I don't know, it may not be moving, But even if it is moving, it's moving in such a way that the net angular momentum is 0. But if you imagine a planetary model of the atom, it has to be moving in a circle even if n is equal to 1 orbital, and it has to have an angular momentum. So it means that motion picture is not consistent with the experimental result and the theoretical prediction. अब zero कह दें कि experimentally कैसे या theoretically कैसे? When we do experiment, we find it to be zero. That's how the nature is. And when we solve the Schrodinger equation, theoretically we see that angular momentum is 0 for n is equal to 1 state. There are several, you can say, reasons, but the most basic one is the uncertainty principle. मैंने पहले भी कहा है, और it would be difficult to fathom for us, and nobody knows the answer to this question, that in 1s, what electron is going. Is it going around like this, or is it stationary? Nobody knows. Yes. Did I say it's stationary? Nobody knows. So that's the question that nobody knows the answer. That what electron is doing in 1s? Is it stationary? Or is it going in a circle? Maybe it's our picture, animation. People have developed different picture. Okay, electron is going like this, or maybe going like that, in such a way that the classical total angular momentum is 0. So you can torture yourself into thinking of different ways of moving the electron in such a way that the classical angular momentum is 0. But even if you construct that picture, that's not going to give you any additional information that we already have from these pictures that are available. So the next, जो असल में ज़्यादा बड़ी mystery है, वो इससे भी आगे. So you can convince yourself in some classical ways. Maybe electron is first going like this, then coming back, going like this, or maybe there's some convoluted way of moving the electron to still make it move and get zero angular momentum, right? But let's go to n is equal to 1 state. In n is equal to, n is equal to 2 state. n2 में एक possibility still zero angular momentum है. लेकिन तो ये n2 state है, इसमें जो 3 possibilities हैं कि angular momentum की magnitude तो है and और same है, but जो z component है उसकी 3 possibilities. So to make a better picture and easier to draw, because I'm used to drawing these things, and perhaps most of you as well, let me draw the z-axis like this. But after drawing this, let me say again, the z-axis is only a label. It can be any axis. So इसका मतलब है कि there are 3 possibilities. One is that maybe the angular momentum vector is oriented this way, or maybe it's oriented this way, or maybe it's oriented this way, such that the z component of this has a certain value, which is what in this case, ये मैं n is equal to 2 की बात कर रहा हूँ. तो इस केस में z component होगा h का, इस केस में z component क्या होगा 0, इस केस में जो इसका z component प्रोजेक्शन इस एक्सिस पे है माइनस h का. लेकिन तीनों सूरतों में जो मैग्नीट्यूड है it is restricted to under root 2 square root h का. n is equal to 2 स्टेज है, आप इनमें से और let's say स्टेज में n is equal to 2 में आ जाते हैं. There are 3 possibilities. Same magnitude, 3 different possibilities of the z component of the vector. और ये तो इतना पार्ट तो क्लासिकली you can still think कि अगर एंगुलर मोमेंटम वेक्टर स्ट्रक्चर में है तो इसका ये z कंपोनेंट होगा, अगर इस स्ट्रक्चर में है तो ये z कंपोनेंट होगा, और इस स्ट्रक्चर में है तो ये z कंपोनेंट होगा. तो there are 3 possibilities. लेकिन जो डिफरेंस है क्लासिकल से वो ये है कि पहली बात तो ये कि आपने जब ये एक्सिस चूज की है there are only 3 possibilities. It can either be this, लेकिन इसमें अलबत्ता there are more than this. So अगर u है ओरिएंटेड या u है या u है या u है, इस सूरत में भी क्योंकि ये जो z पे प्रोजेक्शन है ये सेम है. So if it makes a cone, if it lies anywhere on this cone, the Z component is going to be the same. So the Z component is fixed, but the XY components can be anything. The second possibility is this, that the Z component can be 0. So you can imagine it can be here, it can be here, 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 and anywhere. आप इसमें दोनों possibilities. Either it is like rotating, or it's, I don't know, maybe L vector is stationary here, not the electron, the L vector. And the third possibility is -1, 0 और 1 ये ML की तीन वैल्यूज possible. ये L तो तीनों के लिए 1 है, तो मैग्नीट्यूड तीनों सूत्रों में सेम है. नहीं, इस एक्सिस स्पेस का प्रोजेक्शन 0. हाँ, तो मैं अभी इसके आगे वाली जो है ना उसके साथ आपकी चीज कंफ्यूज हूँ. अब इसका मतलब है एंगुलर मोमेंटम इज क्वांटाइज्ड in such a way that only one component is quantized and the other two components are unknown. They can be any. लेकिन मिस्टीरियस में इससे भी आगे आप लेट्स से दो हाइड्रोजन एटम लें, दोनों n is equal to 2, l is equal to 1 स्टेट में है. इसी तरह से आपने प्रिपेयर किया. एक के लिए आप एक्सेस ये चूज कर, दूसरे के लिए एक्सेस ये चूज कर, और उसके लिए जो तीनों प्रोजेक्शन है वो एग्जैक्टली इसी रूल को फॉलो करें. So the direction of z axis doesn't matter. आप n l is equal to 1 state में atom है, along any z axis it will have only 3 possibilities. तो इसका मतलब है कि जब आपने measurement शुरू नहीं की, you don't know actually where the angular momentum is found. To measure angular momentum, and I'll come to that, how do we measure it? You let's say specify this axis, and to when you start measuring along this, you discover that there are 3 possibilities, either this or 0 or this. लेकिन एक दूसरा बंदा जो है उसी एटम के लिए measure करने के लिए, let's say he takes this as z axis and he tries to find the component of the angular momentum along this axis. So he also sees only 3 possibilities with exactly the same magnitude, h star minus h star 0. जो मर्जी किया. तो इसका मतलब है कि before you measure, you don't know what angular momentum is, okay? And when you start measuring, whatever z axis you choose, you see that the angular moment, the magnitude is quantized. At the same time, we can do that. I'll show you why. Okay? So this is an important question, and this actually has nothing to do with quantum mechanics, because to measure angular momentum of, let's say, a moving charged particle, there's only one way, and that is to use magnetic field. And when you use magnetic field pointing along a certain direction, actually the dipole moment, it starts to rotate in a cone anyway. Even if it has a certain, let's say, x and y component associated with it, as soon as you put a magnetic field, it starts to go in this circular fashion. So experimentally, you can't even measure the x and y component of the angular momentum. Here, आया है श्रोडिंगर इक्वेशन का सॉल्यूशन से जो हमने नहीं. तो जो ये पार्ट है, you have to accept what I'm saying. Okay? The two things that I have written here that you have to accept that they come from Schrodinger equation. So one is the magnitude of angular momentum is that, and the z component of angular momentum is given by ml h star. So this comes when you solve Schrodinger equation. No, मैंने तो नहीं कहा this. We don't know, and quantum mechanics doesn't tell us. And मैं यही point कर रहा था कि classically you can't even measure it. For example, if you have a dipole movement, and a dipole movement manifests itself as a magnetic dipole movement, because whenever you have a current going in a circle, it becomes a magnetic dipole. And to measure the value of the angular momentum, we actually measure the magnetic dipole moment, and to measure magnetic dipole moment, we use a magnetic field. But as soon as we put a magnetic dipole in a magnetic field, it starts to go in this conical fashion. So only its component along B is preserved. Even if it was stationary like this before magnetic field, as soon as we applied magnetic field to measure it, it started to go in a. तो अगर measurement से पहले इसका था भी x और y definite component, तो after measurement it's gone because it's moving in a circle. So there are two things, x और y quantum mechanics doesn't tell us what are those components, और हमें बताना भी नहीं चाहिए, क्योंकि अगर Schrodinger equation ने वो बता दिया इसका x और y component क्या है, so it means you know exactly what is the direction of angular momentum, and if you know the exact direction of angular momentum of a particle in a spherical symmetry, it means the particle is moving in a plane perpendicular to that line, right? If you know that this is the direction of vector L, it means the particle is confined in a plane perpendicular to this. So it means that you know its position with infinite uncertainty along this axis. It can be here or here, but it's definitely constrained inside this plane because L is pointing, and the uncertainty principle will not allow it for a localized particle. So everything is consistent here. Okay, so when we have this quantization of angular momentum, people suddenly started to ये ऐसा सवाल है इसके जवाब में we can spend whole semester. When we are not looking at the moon, does the moon really exist or not? So it's a long philosophical discussion that we don't want to go. In physics and in science now, what matters is what we measure and how can we explain it from the simplest and minimum set of theories, and how we can predict other things based on that theory. Okay, so it's measurement ही हमें affect कर रही है, and the outcome of measurements are predicted by the wave equation from the wave function. Okay, so quantization of angular momentum was actually a radical thing in 1920s when quantum mechanics was being developed, even before Schrodinger equation. So in 1921, there were two people, Stern and Gerlach, who wanted to test if the angular momentum is really quantized. क्योंकि 1915s में बोहर ने भी predict किया था कि angular momentum is quantized, and then from this theory you see the angular momentum is coming out to be quantized. So there was an attempt to measure the angular momentum, and there was a very simple way of measuring if the angular momentum is quantized or not, because people knew one fact from the classical physics, and that fact I am going to review before I come back to this measurement of the quantization of angular momentum. And that fact from classical mechanics is this, which actually turns out to be true in quantum mechanics as well. So from classical mechanics, we know that if a particle of charge Q is going around in a circle of radius r, it forms a current, and that current I can simply be computed as Q divided by the time period of this motion, and if this radius is r, the time period would be 2 pi r divided by velocity. 2 pi r divided by velocity is qv 2 pi r. So this is the current which is given by this moving charge. Now, a moving charge behaves like a small, tiny magnet, moving charge in a circle, and the dipole moment of that small magnet, mu, can be computed as current into area. So for this charge going in a circle, the area is pi r square, the current is here, so qv 2 pi r. This is true in general, it doesn't matter quantum, atomic scale or not. Any particle going in a circle is a current field. Mu is the magnetic dipole moment. So this magnetic dipole moment is current into area. So current area, so this pi cancels, 1r cancels, and then we put, so this is qv R over 2. So let's put an M here and M here, so that this becomes Q 2M, and this MVR is nothing but the angular momentum. So it means that the angular momentum, मैंने वैसे M में लगा दिया कि इसको हम in terms of angular momentum एक्सप्रेस करें. ये यार एक डेफिनेशन, ये डेफिनेशन हमें हेल्प करती है कि जब हमारे पास करंट लूप्स होना मैग्नेटिक फील्ड, हम थोड़ी देर में देखेंगे, तो उनकी इंटरेक्शन आसानी से हम समझ सकते हैं if we convert it into an equivalent magnetic dipole, और उसका मैग्नेटिक डाइपोल मूवमेंट जो है we define it like. Unfortunately आपने इलेक्ट्रिसिटी मैग्नेटिज्म में भी पढ़ना है, you can just take it as a face value. तो ये आप देखें, ये जो मैग्नेटिक डाइपोल मूवमेंट है एक इक्विवेलेंट टाइनी मैग्नेट का in terms of the mechanical quantity, ये देखिए ये इलेक्ट्रोमैग्नेटिक क्वांटिटी है, ये मैकेनिकल क्वांटिटी. हमने इस मैकेनिकल क्वांटिटी को इलेक्ट्रोमैग्नेटिक क्वांटिटी से रिलेट कर दिया to this Q and M, and this actually turns out to be true for orbital motion even in the quantum mechanics. और इसका मतलब है कि अगर आपने इसकी क्वांटाइजेशन टेस्ट करनी है, which we have no way of going, especially in 1920s, going to the atomic level and trying to see what electron is doing, कि उसका एंगुलर मोमेंटम सिर्फ यही पॉसिबल, ये डायरेक्शन ही पॉसिबल है या इसके अलावा भी. So you measure indirectly, instead of measuring the mechanical quantity, you measure this dipole moment, because this we can measure with a bigger setup. We can probe the magnetic dipole using magnets out of the in a bigger setup. Yes, मैंने कहा है कि this is the classical result, which fortunately turns out to be true in quantum mechanics as well. There is a quantum mechanical way of relating the angular momentum to the magnetic dipole moment, which unfortunately we can do, which we can do actually using the wave function. तो ये मैंने एक आपको थोड़ा intuition देने के लिए, जैसा classical mechanics में we have a revolving particle whose angular momentum is related to its magnetic dipole. So the same thing is true in the quantum mechanics as well. हाँ, इस केस में डेफिनेटली जरूर क्रॉस, लेकिन हमने उसको छुपा दिए एंगुलर मोमेंटम. हाँ नहीं, अब देखिए आप जानबूझ के साथ बहुत कुछ स्ट्रेच करते हैं. मैं उस नेगेटिव सेंस में नहीं कह रहा, इस सेंस में कि आई सेज कि दिस इज ट्रू इन क्लासिकल मैकेनिक्स, in quantum mechanics it turns out to be true. The velocity में ये रिलेशन, जो ये रिलेशन है, the mu is Q 2ml, this is true in quantum mechanics as well, that the angle which we derive here classically, okay, because we haven't found the wave function. From wave function we can relate the magnetic dipole moment to the angular momentum, but of course we are not doing. So you will have to take this on my word that this is true here. But that concept of quantum mechanics is still valid. हम ये तो नहीं कह रहे कि यहाँ से लेके आ रहे हैं, so now we are going to abandon quantum mechanics. Okay? अगर आप एडवांस क्वांटम मैकेनिक्स पढ़ना चाहते हैं तो आई कैन डू दैट फॉर अ सेपरेट कोर्स. ओके, yes I did for circular orbit. Everything here is valid only classically. The final result, which is a relationship between angular momentum and magnetic dipole moment, turns out to be correct in quantum mechanics, which we are not driving. Logic roughly same है, that there is an angular momentum, and angular momentum roughly means a spherical motion. So because of angular momentum, it means moving charges, which roughly corresponds to magnets. Okay, circularly moving charges. So there is a magnetic dipole moment. I know it is a bit uncomfortable, but that's the nature of the thing. Okay. The, let me do one other thing in 5 minutes as a break. So if you have a magnet, okay, and there is a uniform magnetic field. Uniform means it's the same here, same here, same here, same here, same here. And if you put a tiny magnet here, what's the net force on this tiny magnet? What's the net force on this tiny magnet? Numbers will go. Why? मैंने कहा कि constant uniform field. हाँ जो situation इधर वो situation इधर. It's a uniform field. So the net force is zero. It's neither going there, it's neither going here. Okay, so let's say this is being repelled in this way, but then this is being repelled like this. This may rotate, that's a separate thing, that's a torque. But when we say force, it means the translational force. So the net, there's no net translation. So when we put a small magnet in a uniform field, there's no force on a small magnet. But if we create a field like this, so this is a short band, so there's a magnetic field like this, and let's say this is the south pole, this is the north pole, and now if I put another small magnet here, now it will feel a net force either this way or this way depending on this SN. इस केस में अब यहाँ पे strong field है, यहाँ पे weak है, मतलब है this is more attractive and this is less attractive. So in the net forces in the upper direction. So this is repelling it and this is attracting it. This is ये इसको attract कर रहा है, ये इसको repel कर रहा है. So थोड़ी सी rotation होगी, ठीक है? So forget about rotation. In terms of translation, there is a net force in the upward direction. और अगर ये north हो और ये south हो, so there is a net force in the downward direction. अब ये देखिए यूनिफॉर्म फील्ड में एक स्मॉल टाइनी मैग्नेट है, ये मैंने बड़ा बनाया, यू कैन इमेजिन इट टू बी अ वेरी टाइनी वन. तो और अगर यूनिफॉर्म फील्ड है, देयर इज नो नेट अप एंड डाउन फोर्स. लेकिन अगर नॉन यूनिफॉर्म मैग्नेटिक फील्ड है, तो देयर इज अ फोर्स, नेट फोर्स आइदर दिस वे और दिस वे डिपेंडिंग ऑन एस एंड एन. तो अगर जो हमारा टाइनी मैग्नेट है, इफ इट इज पॉइंटिंग दिस वे, so s1, so this the dipole movement. So if the dipole movement, let's define it to be pointing from N to S. If it is like this, then it feels a force in this direction, and if there is a dipole small magnet like this feels a force in this direction. So again, इस तरह का region हो, and you send a lot of tiny magnets to this field, तो ये क्या होगा? ये उनको separate कर देगा. जो मैग्नेट इस तरह कर रहे होंगे उनको इधर भेज देगा अगर मैग्नेट्स यहां से चलते आ रहे हैं, और जो मैग्नेट ये NS वाले हैं उनको ये इधर कर. So this non-uniform magnetic field can be used to separate these two types of tiny magnets which are pointing in different ways. So this was the concept that was used by these people in 1921 using silver atom, but instead of that we will use hydrogen atom, which experiment was done in 1927. And what they did, they took hydrogen atoms and passed them. So they have hydrogen atoms. They passed them through a non-uniform field, and they put all hydrogen atoms in the ground 1s state. So one or असल में at that time the spin thing, जो individual particle है, that was not discovered, जो भी हम ने discuss किया. So this is what was roughly known. So they had the hydrogen atom in n is equal to 1 state. So they were expecting that the hydrogen atom would have zero angular momentum. So when you pass lot of hydrogen atoms, a stream of atoms from here, and you have a screen here, you should see all of the atoms going here. क्योंकि वन एस स्टेट है, वन एस स्टेट का एंगुलर मोमेंटम जीरो है. अगर एंगुलर मोमेंटम जीरो है, एल जीरो है, तो म्यू क्या होगा? जीरो. So they expected to see all of the atoms go here. But what they saw was completely different. They saw that the hydrogen atoms are going either here or they are going here. यहां से अभी तक हमने जो भी किया है N1 स्टेट में एंगुलर मोमेंटम इज तो दिस वाज अ शॉक. When you take hydrogen atoms which are neutral, okay, and you pass them through here, and since they are in 1s state, they should have zero angular momentum associated with them. So zero angular momentum means this non-homogeneous magnetic field should not deflect them either this way or that way. They should go straight. But instead, they went either here or here. मुझे बात पूरी तो करते हैं. तो अभी जो कहानी है वो चल रही है, अभी बात खत्म हुई. Okay, so this was a shock. So this forced people to another conclusion that there is another source of angular momentum. Yes, and that new source is what we call the intrinsic spin. So there's another source of angular momentum or magnetic dipole moment. It's the intrinsic spin of particle. And you can actually explain this fully using relativistic quantum mechanics. And I'm just going to state the result of that. So the idea was this, that the electrons have an intrinsic spin associated with them. अगर आप अपने दिन में रॉन्ग पिक्चर इमेजिन करना चाहते हैं, you can think of this electron as a spinning top. And अगर आप जो correct picture develop करना चाहते हैं, तो you can forget about what the electron looks like and simply think of the spin as a property of electron, just like you think of charge. आप कहते हैं electron को negative 1.6 इतने coulomb charge. Have you ever tried to think of a picture of that charge? So you have to think of spin in exactly the same way. That this is intrinsic property of the particle. उसको spin इसलिए कहते हैं कि this corresponds roughly to that classical concept. और असल में अब जो मैं आपको अभी जो concept दे रहा हूँ, this is what is the agreed upon concept nowadays. Initially, people tried to explain it as a spinning thought. They try to compute the angular momentum for electrons and protons by modeling them as spinning spheres. And everything turned out to be incorrect. So that's why the current accepted interpretation is this, that it's an intrinsic property of this particle. And for us, it doesn't matter कि वो property वो spin होने से आ रही है या कैसे आ रही है. Charge का कैसे समझ आता है? कैसे समझ आता है? The field oscillations charge कैसे? ये बोझ आता है, फोटॉन भी बोझ आता है, दोनों का charge. ये इलेक्ट्रॉन का charge कैसे समझ आता है? सिर्फ इसलिए होता है कि आप काफी देर पहले से 5-6 सालों से चार्ज होते हैं. It's just like religion. When you're born, if you're born in a certain way, you're taught one thing again and again, you begin to accept it. Okay? If you come to something else later on, you start question. So the charge is the same thing. You start learning about charge when you are 4-5 years old, maybe 6-7 or little bit later. Or also, since you are forbidden to ask questions, where this charge comes from, you begin to accept it because people are telling you. And now you are used to that thing. But since the spin is coming for the first time, and this is independent intrinsic property. Which particle you can explain? For example, proton, I can explain where the spin of proton comes from. It comes from the total spin of the quarks that make up the proton. But where the spin of proton comes from, the quarks comes from, it's intrinsic spin. So electron is one of those what we call fundamental particles. We don't know, and we don't care, and it doesn't matter. Yes, or you have, if you can understand the meaning of this thing, you begin to understand quantum mechanics. Okay, जो combined particle, that's the hydrogen atom. So hydrogen atom are, let's say, more complicated atoms. They also have a net angular momentum, which you can explain, because you can explain them as a vector sum of the individual angular momentum. But the spins or angular momentums of fundamental particles, they are the intrinsic spins, and you can actually get, let me correct myself a little bit. Still, you won't be able to say if it is spinning or not, but you can see the origin in relativistic quantum mechanics. Because it's naturally, when you solve the Gerlach equation for fundamental particles, you naturally find that there have to be two types of spins. You are able to see where they're coming from, but still you can say if it is spinning or not spinning. Okay, so this is, it means that there is another source of angular momentum, and it's called spin, and it behaves similar laws as the orbital angular momentum, and that is that its magnitude is given by a spin quantum number h cut, and its Z component is still quantized in the same way. This is called spin magnetic quantum number h cut, and ms still has the same dependence on s like this, but there's only one difference. जब आप orbital angular momentum की बात करते हैं, L can be 0, 1, 2, 3 or so on, but here this small s, it can have only one value for one particle. For electron, this s is half this small s, so it means ms can only have two values, minus half and plus half. It has to go from minus s to plus s. So minus half में जब आप 1 add करते हैं, you quickly jump to s. So for electron, it's minus half and half. So there are two spin states possible for electron. Its spin can have either a minus half d component or a plus half d component. So with this additional angular momentum, we can now explain the result of Stern-Gerlach experiment for hydrogen. So now you can see why they didn't go to one way. क्योंकि 1s orbital में इलेक्ट्रॉन था, उसका orbital angular momentum 0 हो गया, but इलेक्ट्रॉन का अपना तो angular momentum है ना, which would be either minus half or plus half. So it means the angular momentum associated with the spin angular momentum still has a value. आप चूंकि और अगर आप since this s has this magnitude and sz, अगर मैं z component सिर्फ लिखूं angular momentum का, so the z component now has two values, because this sz can be either half h cut or it can be minus half h cut. तो इसका मतलब है जो net angular momentum है इलेक्ट्रॉन का उस ऑर्बिटल में, the net angular momentum is let me represent it by j. It is L plus s. This is 0, but this is not 0. So total angular momentum क्या होगा? Orbital angular momentum plus spin orbital angular momentum. अब 1s स्टेट में ये तो 0 हो गया, लेकिन ये नॉन 0 है और इसकी कितनी वैल्यूज पॉसिबल हैं? इसके z कंपोनेंट की दो वैल्यूज पॉसिबल है, क्योंकि s z जो है वो minus half h cut है या plus half h cut. So that's why the atoms, some of them went up, which have a plus half h cut angular momentum, and some of them went down, which have the negative of h cut angular momentum. J is the total angular momentum. roughly if you are getting those hydrogen atoms randomly, they will go half of them out. तो Stern-Gerlach से उन्होंने एक्चुअली एक्सपेरिमेंट किया था सिल्वर के साथ और they took silver atom, neutral silver atom, which have all shells closed, but there is an electron, single electron in 3s orbital, or that actually behaves exactly same like the hydrogen atom, because in 3s orbital still the angular momentum is 0, and the vector sum of all internal electrons are also 0, which meant that there was only an angular momentum due to a lone electron in 3s orbital for silver, and they also did that. They also went half of them up, half of them down. जी ये half क्यों होता है? So the answer comes from relativistic quantum mechanics, which we are not. Sorry. Spin, as far as I know, there is nothing. For example, proton and neutron, they are also spin half particle. When we say spin half particle, it means this value of small s is half. Photons have a spin 1, that their s is equal to 1, and similarly the other particles, for example, boson, W boson, they have spin half. So, हम ज़्यादातर वैसे इलेक्ट्रॉन के साथ काम करेंगे, which has a spin either minus half or a spin plus half. Now, let me come back here. This thing, that energies of all electrons in n is equal to 2 orbital orbit are the same. Can we do something to distinguish if the electron is here or here or here? We can, by putting the atoms in a magnetic field. Because when we have a magnetic dipole movement in a magnetic field, let's say there is a magnetic field B along Z axis, and there is a tiny magnet with a magnetic movement mu, then its potential energy in the magnetic field is given by minus mu dot B. So unfortunately, these results come from electricity magnetism. So you can just accept it like the Coulomb law for magnetic dipoles. So a magnetic dipole has a potential energy U like this in a magnetic field. So this is the magnetic field that is pointing along Z axis. Z hat is the direction of Z unit vector. So इसका मतलब है, so this potential energy is minus mu Z bz, because if this is only along Z, आप mu का इसके साथ dot product ले, you only get the Z component. So when this is the potential energy of a dipole in a magnetic field, it means the potential energy of an electron. Let's say I consider a hydrogen atom, and you imagine that this hydrogen atom now exists in an external magnetic field, which means the energy of this electron is now sum of the three energies. The total energy of the hydrogen atom is now sum of the energy En, which is given over here, plus it is the energy due to the En is the energy in the nth orbit, in the nth shell. So this is the energy mu ZL, mu sub ZL into Bz due to the orbital angular momentum, and then this is the energy due to the spin angular momentum. Or again, I expand a little bit further. And so जो potential energy है magnetic potential energy, वही बात है. जो magnetic potential energy है is dot product of dipole movement and magnetic field. इनका dot product ले तो B सिर्फ Z के अलग है, तो सिर्फ mu Z bz आ जाएगा, ठीक है. और mu Z जो है, अब चूंकि इलेक्ट्रॉन के दो एंगुलर मोमेंटम है, ऑर्बिटल एंगुलर मोमेंटम और उसका स्पिन एंगुलर मोमेंटम. मैं सारा ऐसे कर रहा हूं, बट यू नो दैट आई डोंट मीन इट. ओके, गुड. तो अब इस ये जो डाइपोल मूवमेंट है, इसका फार्मूला क्या होगा? Q 2me LZ, okay, because if mu vector is this, so mu z is Q2M LZ, so Q2ME LZ into BZ, और mu SZ जो है, now अब मैंने आपको ये नहीं बताया कि how is the S angular momentum related to the magnetic dipole moment of the electron. So ये तो angular momentum है ना, तो इसका जो magnetic dipole moment है, unfortunately now there is no classical counterpart कि मैं जिसका रिजल्ट ड्राइव करके आपको कहूँ कि वो quantum mechanics में भी true है. But there is a similar relation, and let me simply write it. Mu z due to spin is some coefficient g e over 2me into s. और ये जो g है इसको कहते हैं g फैक्टर या gyro-magnetic रेशियो. ये डिफरेंट पार्टिकल के लिए भी डिफरेंट होता है. फॉर एग्जांपल इलेक्ट्रॉन के लिए इसकी वैल्यू तकरीबन 2 है, प्रोटॉन के लिए इसकी वैल्यू 5 पॉइंट समथिंग है, न्यूट्रॉन के लिए कुछ और है, डिफरेंट पार्टिकल के लिए इसकी वैल्यू कुछ और है. तो जो डाइपोल मूवमेंट है उनके दो ऑरिजिन हैं, एक स्पिन और एक ऑर्बिटल एंगुलर मोमेंट. जो स्पिन वाला है q/2 mass Lz, जो ऑर्बिटल जो स्पिन है इट इज g q, तो s z b. हाँ जी आप बताएं. ये वैसे g का फैक्टर भूल गया. बिल्कुल. न्यूट्रॉन जो है उनका मैग्नेटिक डाइपोल मोमेंट 0 बिकॉज़ चार्ज इज 0. जी कुछ भी हो बट चार्ज इज 0. ओके, अब इसको लेट मी गो बिट फर्दर. So let's have a deal. Okay. So 5 minutes, and anybody who's present here will get 5 points in the present homework. फिर आप लोग सौदा करना चाहते हैं तो अच्छा सर इस तरह से हो नहीं, मीटर में नहीं, क्योंकि 1% marks in the course who are present today for 10 minutes. कोई टीए है जो भी अटेंडेंस ले सके तो प्लीज सर. नहीं, that's too much. क्योंकि जिन लोगों ने वीडियो देखी है वो कहेंगे हमने भी 10 मिनट ज़्यादा देखी है. ठीक है. नहीं तो फिर जाती हो कुछ लोग हो किसी मजबूरी से ना आ. 1% इज माई डील, जो जाना चाहे वो जा सकता है. ओके, सो असल में ये जिस क्लोजर की तरफ मैं जा रहा हूँ, दिस इज सो इम्पोर्टेंट एंड मे बी फॉर सम ऑफ यू इट माइट बी रिवार्डिंग टू सी व्हाट्स द इफेक्ट ऑफ these orbital angular momentum L and ML and MS on the energy levels in hydrogen atom. So let's continue little bit. इसमें अगर आप देखें तो जो टोटल एनर्जी है दिस इज En, ये Q की वैल्यू है -E, तो ये प्लस हो जाएगा, ये कॉमन आ जाएगा, ये भी कॉमन, ये भी कॉमन. और LZ की वैल्यू क्या है, LZ है और BZ भी कॉमन आ जाएगा. LZ है ML into, so this LZ, what is LZ? ML H cut, and what is SZ? ms h. So let's take h cut common as well. So e h cut, वो चार्ज जो है ना वो q माइनस e है तो माइनस कम्स पर, तो bz ml, और ये g है दिस इज रफली 2 for electron. So let me put it. Now you see this is the total energy when you put a hydrogen atom or any atom, any single electron atom in an external magnetic. तो इसका मतलब है कि अब अगर आप n is equal to 1 को देखें तो पहले क्या होता था, n is equal to 1 में सिर्फ एक ही एनर्जी, अब n is equal to 1 में कितने एनर्जी लेवल पॉसिबल है, यहां से देखिए ml की कितनी वैल्यूज पॉसिबल है, एक, n1 है, n is 1, so ml is only 0, ms की दो वैल्यूज पॉसिबल, प्लस हाफ और माइनस हाफ. अगर आप थोड़ा कंपैरिजन करना चाहें ना तो ये En अगर हाइड्रोजन के लिए मैं लिखूं तो दिस इज 13.6 इलेक्ट्रॉन वोल्ट इन n1 माइनस 13.6, और ये जो नंबर है ना ये वाला नंबर, दिस इज कॉल्ड बोहर मैग्नेटॉन, और इसकी वैल्यू है रफली 6 into 10 power minus 5 इलेक्ट्रॉन वोल्ट पर टेस्ला. अब फर्ज करें कि हम किसी ऐसे स्टार पर हाइड्रोजन एटम से आने वाली लाइट को देखते हैं जहां पे 1 टेस्ला मैग्नेटिक फील्ड मौजूद है, तो अगर V1 टेस्ला है तो ये सारा नंबर कितना हो गया, 6 10 पावर माइनस 5 इलेक्ट्रॉन. अब जो लोएस्ट लेवल है उसमें एक एनर्जी होगी माइनस 13.6 प्लस दिस नंबर, जब ms प्लस हाफ है, और जब ms माइनस हाफ है तो माइनस दिस नंबर. तो इसका मतलब है there are two possibilities for energy level, for energies when n is equal to 1. This is energy per Tesla and this is Tesla, so Tesla cancel with Tesla. Okay, ये बात किसको समझ गया? ये इलेक्ट्रॉन चार्ज, प्लैंक कांस्टेंट, मास ऑफ इलेक्ट्रॉन की वैल्यूज पुट करें तो ये नंबर आ जाता है 6 into 10 power minus 5. तो इसको नाम दे देते, नाम ही नाम दे दो, डजंट मैटर. ये कांस्टेंट है, इस वैल्यू इज दिस. ml and ms are quantum numbers, so they are just numbers, they are unit. ये g की वैल्यू इलेक्ट्रॉन की है, this is the experimental value, but theoretically we can find it using relativistic quantum mechanics. जब इलेक्ट्रॉन का चार्ज नेगेटिव होता है तो मैंने q की जगह पे माइनस ई रखी, ठीक है, माइनस ई तो माइनस माइनस प्लस. g इज gyro-magnetic रेशियो के किस रेशियो से जो एंगुलर मोमेंटम है वो मैग्नेटिक डाइपोल मूवमेंट में कन्वर्ट होगा. ओके, so this is for ms is equal to half, actually minus half, नहीं ये प्लस हाफ होगा तो इसमें हाँ ये प्लस हाफ के लिए, और जो ऊपर वाला है दिस इज माइनस हाफ. अब ये n इक्वल टू 1 लेवल, जो n इक्वल टू 2 लेवल है उसमें क्या पॉसिबिलिटी है, ml 0 हो सकता है, ml 0 तो इसकी दो वैल्यूज हैं, तो जो इसका सेकंड एनर्जी लेवल है n इक्वल टू 2 वो कंप्यूट करें और उसमें से ये नंबर आप प्लस माइनस करें, so you get 2 levels. And then when ml is equal to 1 and ms can still be plus minus half, तो आपके पास दो लेवल और आ जाएंगे. And when ml is minus 1 it can still be plus minus half, और दो लेवल और आएंगे, लेकिन इन दो में से एक वही होगा जो पहले था, क्योंकि जब ml प्लस 1 है तो ms जब हाफ है, तो जब ये माइनस 1 है और ये प्लस हाफ है दे कैंसिल टू 0, एंड व्हेन क्योंकि ये माइनस 1 है तो ये प्लस 1 बन जाए. और सोच भी लिया करें यार बोलने से पहले, when this is plus 1 and this is minus 1 they still cancel out. तो इसका मतलब है कि जो दो states हैं they have the same energy and that energy is equal to only this one. So there is a central line corresponding to two states and then there are two lines here and two lines here. हाँ, तो माइनस, जब ये माइनस और ये माइनस है, you go to this point. तो -1 and -1 -2 बन गया, इसको -2 से मल्टीप्लाई करें, ये माइनस समथिंग है उसमें ऐड हो जाएगा न्यूमेरिकली एंड यू गेट टू दिस लोएस्ट एनर्जी. तो जब ये +1 है तो ये माइनस भी हो सकता है और ये प्लस भी हो सकता है. ये दो है. ये देखिए मैंने 5 लेवल ड्रॉ किए, तो टोटल 6 बनते हैं, क्योंकि ml 0 होगा तो इसकी दो वैल्यू, दो लेवल, ml 1 पे दो लेवल, ml -1 पे दो लेवल, लेकिन दो लेवल से उनकी एनर्जी सेम होगी, दो स्टेट, ये प्लस और ये माइनस और ये माइनस और ये प्लस होगा, तो इसलिए टोटल 5 लेवल. हाँ, तो एक वो है और एक दूसरा है, तो दोनों स्टेट का सेम होगा, तो ये टोटल 6 पॉसिबिलिटीज है. ठीक है, 6 में से 2 पॉसिबिलिटीज का सेम है, तो टोटल 5 लेवल का. अब देखिए, फर्स्ट करें, आप लाइट देख रहे हैं एक ऐसे स्टार से आने वाली जिसके हाइड्रोजन एटम जो है वो एक्सटर्नल मैग्नेटिक फील्ड में, तो आपको उसका स्पेक्ट्रम कैसे नजर आएगा अगर इलेक्ट्रॉन सिर्फ इस लेवल से इसमें ट्रांजिशन करे. अगर कोई मैग्नेटिक फील्ड नहीं है तो इसका एक लेवल था, इसका एक लेवल था, और आपको जस्ट एक लाइन नजर आ रही. और अगर आप तो एक की बजाय 5 या 6 लाइन नजर आए, जैसे फर्ज करें एक ये एनर्जी लेवल है, ठीक है, एक ये है, फिर एक ये है, और फिर ये और ये अब दोनों की सेम वेवलेंथ होगी क्योंकि ये डिफरेंस और ये डिफरेंस सेम है, तो यहां से यहां और यहां से यहां सेम है. बट you can see, I think there are 5 wavelengths that are possible. So this is the possible wavelength that you will see for transition for n equal to 2 to n equal to 1. और ये जो डिफरेंस है इनके दरमियान, क्या इससे आप इस स्टार पे जो मैग्नेटिक फील्ड प्रेजेंट है वो कंप्यूट कर सकते हैं? कर सकते हो, आपको करना पड़ेगा. ठीक है, किसी होमवर्क में या किसी एग्जाम में, बाय डूइंग बैक सब्स्टिट्यूशन, के जितना ये मैग्नेटिक फील्ड स्ट्रांग होगा ये नंबर उतना बड़ा होगा. ठीक है, क्योंकि ये तो कांस्टेंट है और ये वही 1 और 0 और इसी रहने, तो ये जितना बड़ा, जैसे ये 1 टेस्ला की बजाय 10 टेस्ला हो जाता है, सो दिस बिकम्स 10 टाइम्स. और ये जो डिफरेंसेस हैं एनर्जी लेवल में इजीली ज्यादा बड़े हो जाएंगे, तो ये जो वेवलेंथ्स के अंदर जो डिफरेंस है दिस विल बिकम बिगर. And using this technique, people have been able to measure magnetic fields on stars that are billions of light years away from us, or black holes, or neutron stars, which can actually have magnetic field as strong as 1,000 Tesla, or maybe 10,000 or a million Tesla. Such strong magnetic field. We can, and you see, we can do all of this while sitting on Earth, by doing all of this calculation. So let me just summarize in 1 minute because I asked for 10 minutes. That electrons in orbits have an angular momentum due to quote-unquote orbital motion, and that angular momentum gives rise to magnetic dipole moment, and then electrons have an intrinsic angular momentum, quote unquote, due to spin, it's called spin, and the net angular momentum is a sum of the two angular momentums, and the net magnetic dipole moment is also the sum of the two magnetic dipole moments, and they are both movements are quantized, and because of that, the electron, the atoms, when they are placed in external magnetic field, their energy levels are split, called actually Zeeman effect. And because of this splitting of energy levels, the light that comes out of them can now have more than one wavelength even for these two transitions. एक ऑर्बिटल पे, so this is a good question कि एक ऑर्बिटल पे इलेक्ट्रॉन की दो स्पिन्स क्यों होनी चाहिए, और जो नेक्स्ट क्वेश्चन है, जो नेक्स्ट लेक्चर है, that's fully going to be dedicated to this question. Okay, so no, not for this, because we know the answer. Minus? Okay, so you can go. We don't need attendance. I'll give 1% to everyone because people are listening. Acha? Junaid? Yeah, you get attendance please. I think it does. Actually, the grades in this class are decided by